Hello everyone, my name is Zhuo and I'm a PhD student from Norwegian University of Science and Technology, Department of Mechanical and Industrial Engineering. Today I will be presenting my research topic, Scale Effect on the Mechanical Behavior of PLA specimens fabricated via Fused Deposition Modeling. I would like to take this moment to thank Rakel and my supervisor, Razavi, for their assistance. I couldn't accomplish this research without assistance from them. This is the outline for this presentation. First, I will be talking about background motivation and some literature reviews. And next, I will be talking about FDM fabrication process as well as experimental procedures. And then, some results and discussions will be talked about, and finally is the conclusions. So the aim for this presentation is to investigate the influence of the thickness of PLA specimens fabricated via FDM technology on their mechanical properties. So let's talk a bit about the background of additive manufacturing. So the fundamentals and the working principles of AM additive manufacturing offer several advantages, including the superior design and the geometry flexibility. And it is as a new industrial revolution, and it has many techniques. And for this research, we'll be focusing on the FDM, which is Fused Deposition Modeling. Okay, so for the motivation of this research, first, in general, mechanical properties of the components produced with AM are very dependent on the geometry and scale of the fabricated part. So any changes in the geometry will influence the inherent characteristics such as internal porosity residue stress. So therefore, it is very important to understand the connection between the mechanical properties of these components and their geometry and scales to improve the manufacturing process and the applications. And these are the test specimens for the dimensions we have selected. So according to the ASTM standard tensile test, we have selected type 1, and these are all the dimensions for the test. And for the fabrication process and test measurements, for the printers, we have used Prusa i3 MK3, and for filament, we chose the 3D net. The color is natural, and the diameter for the filament is 1.75. And for the slicing software, we used Ultimaker Cura 4.8.0 to slice the specimen. So this is all the dimensions for the standardized specimen. It has the thickness of 3 millimeters. So for this case, we treated this one as 100% scales, and we need to scale down to 50% as well as 30% to make a comparison for the scale effect. So this is the specimen fabrication and the process parameters. As you can see from the process parameters, we have made some trials and errors to determine the best the process for fabrication in order to make it 100% infill as well as the smoothness on the surface. So these are some of the properties for all the specimens we have. So for the standardized one, we have the cross-sectional area of 39 millimeters square, and the gauge length will be 57. And for the 50%, we times 50 with the length here, and for the 30% we scale down according to the scale. And this is the solid space. This is the printing orientation, how we place the specimen in the software. And this is the Tensile test machine and the parameters we have used for this research. We have used the MTS Tensile test machine model 42. It has the maximum capacity of 5 kilonewton loading cell. And for the sampling rate, we have selected 10 Hertz, which means we are collecting 10 data per second. And for the tension rate is 2 millimeter per minute. And for the fracture surface, we used optical microscope to examine it. And these are the results from our test. And as we can see from the table on the left and the plots on the right. So when the scale increase, the yield strength as well as the ultimate tensile strength also increase. So for Young's modulus, it kind of stays the same with a certain fluctuation, and for the elongation, it also increase. And this is the specimens, how the specimen look like after fracture. As you can see, some of the fresh specimen got broken near the edge of the gauge length, and some of them were broke in the middle. And all of them has a shape of horizontal lines for the breaking. So none of them follow the raster angles, either with plus or minus 45 degrees. And this is the one possible reasons to explain why some of the specimens have the fracture position near the edge of the gauge length. So for each layer, for the printing, for the Cura software, instead of starting from the end, it actually starts somewhere in the middle for every single layers. So that may cause some defects in here. And we can make assumption here. The dimensions of the voids are identical for each scale because the same process parameter were used in this case. And this is how the fracture surface look like under the microscope. As you can see, with the increase of the scale, there's a tendency to have less defects and voids on the surface. This is the digital image correlation DIC for doing the analysis. So in this case, we have selected subset as 29, which means the tracking area of the dots for using the DIC was 29. And the larger area it gets, the larger tracking area, but also with the less uncertainty. And we have selected step 7, which means for every 7 data, the software took the average and used the average data for the calculations in order to save the computational time. And for the Y label here, we have EYY, which means the string in the Y direction. So positive numbers indicating the tension here. And as long as I can play these videos, as you can see, the displacement starts approximately somewhere in the middle. As you see, the color changes in here, and there is some more deformation here, and propagates to the both sides. and eventually it will stop and has the highest stress concentration in this area. So this area tends to have the high possibility to be broke. And this is how we calculate Poisson's ratio. By doing the analysis, we selected the small area, rectangle area in the middle, and then we can calculate the Poisson's ratio based on that. And another DIC image, as you can see. So this the image for the DIC here has the highest concentration for the stress or for the strain, and this is the place that's going to break. Same applies for this DIC image. Okay, so now we can make a conclusion. So first, specimens with downscaling experience both smaller ultimate tensile strengths and lower elongation and failure, as well as the yield stress due to some possible reasons. First is the first layer quality. As you can see, especially for FDM process, the quality for the first layer is very important, and it's affected by so many factors. So that's why first layer quality has the influence on that. And second is the possible weak spot near the edge of the gauge length, as I showed earlier. So if we make assumptions of for every scale we have the same defects, then relatively for larger scale we tend to have less percentage of the defects and the voids. So that's why the elongation gets higher as well as the ultimate tensile strength when scale is getting larger. And second, it is possible that specimens tend to have more defects and voids per volume when the downscaling according to the fracture image from the optical microscope. So we haven't done a true analysis for the defect analysis for the microscope, but this is the hypothesis we have. And third, the standard deviation of mechanical properties like elongation failure, yield stress, UTS increase when downscaling due to the following reasons. First could be the uneven temperature distribution on the plate. When we printed all the samples, we lay out for each test we have at least 5 of them, so we laid all of them on the printer to print. So that might cause some uneven temperature distribution on the building plate. And next, there's a higher possibility of misalignment when testing. So especially for the scale of 30%, the specimen gets really small for testing, and there's a very high possibility if you have a misalignment, you're not putting the specimen vertically on the testing machine. Okay, that's the end of my presentation. Thank you for your attention, and if you have any questions, please contact me.